Well, I was scheduled to talk first, and then Professor Davor Pavuna was supposed to be next, but he is on his way to airport right now, and he asked me to actually cover for him. So I'll try to combine what the two of us had to say into one thing. It was a difficult task because the conference had 4 parallel sessions, so clearly I couldn't listen to everything. And you will see that some of these things were added in the last minute, literally, like talk of Professor Haiku Van was just before this plenary. So this may not be as coherent as I would like it to be, but I'll do my best. So one thing that a number of speakers pointed out in the high TC line was that we all believe that the high temperature superconductivity in cuprates is an important problem, perhaps the most important problem in condensed matter physics today. And by the high TC problem, what we really mean is what is the origin of the high temperature superconductivity? What is the microscopic mechanism of high temperature superconductivity? But one can debate even whether it is an open problem or not, because quite a few people have claimed from as far back as 87 January or February is to have solved the problem. And the problem is that there are hundreds of such proposals and they are orthogonal to one another. So not all of this can be true. Now, at this conference, probably because of the great, fantastic location and the great food and interesting program, the atmosphere was non-confrontational, unlike in the early days of high TC or say in the Bell Labs. But while we can have different opinions, you know, and still be friends and sit together, the ideas actually clash. So the explanations that were proposed, and there are only some of these that I've listened here, are actually not compatible with one another when you just give it a little critical look. So part of the confusion or disagreement may be in the semantics, and this question was raised by Professor Sunko earlier. So I'll try to define, you know, at least how I use these words, and I'm trying to follow the majority, the crowd, when it comes to semantics. So a BCS theory or orthodox BCS theory is the theory as formulated by BC and S. And if I want to be generous, you could include Bogolyubov and Migdal and Yashberg and Gorko and so on. The characteristic is that it starts from a Landau Fermi liquid theory, and then you add a weak retarded electron-phonon coupling that produces a weak pairing interaction, and it causes an instability in the Fermi liquid below some temperature, at which two things occur at the same time: electron pair and condense. Now these pairs are large. They are in K-space, they are entangled, and they overlap very densely. There are very many pairs in coherence volume. And since they are all entangled, in the density of states appears a collective gap. And it's collective in the sense that it depends on how many pairs do you have. If you break pairs, then the gap shrinks. Now, you could formally replace in the same formalism phonons by some other bosonic excitation like excitons or magnons, and that was done long ago. But there are some problems. One is that in superconductors are metals in normal state, and in metal there are no excitons. When you create an excitation, you excite an electron, you leave a hole, but the electron goes one way and hole goes the other way. However, Ginsburg argued 60 years ago that maybe this could still work at metal to semiconductor interface. The electrons that are next to the surface could interact with excitons which are right on the semiconductor side. However, this was never observed experimentally in a convincing way. And then we have the BC theory, which starts from small electron pairs that are compact and behave, and they are far from one another, so they don't overlap. Therefore, they behave as bosons. What is characteristic here is that to have that, you need a very strong unretarded pairing interaction. Then you will have a local bound pair state. So the gap, the pairing gap that you will see in the spectroscopy and density of state is actually property of individual pair. It's local rather than collective, which means that upon pair breaking, the gap will not shrink, but it will fill in from the bottom up. And you will have pairs present well above the coherence onsets at TC in the system, and you have server gap, etc. And again, this was never observed experimentally in very convincing to everyone. Now we have also this BC-SBC crossover, and the idea, I think, was probably first proposed by Eagles, but more powerful, influential work were done later by Tony Leggett and Philippe Nozier and Schmidt-Rink. And more recently, this was pushed by Mohit Randeria and Kathy Levin, and experimental by Neil Harrison. There was a PRL-sponsored talk very recently about experimental data that favored something like that. Now, this is another, and one axis. The other one is, Fermi liquid versus doped Mott insulator. What is doped Mott insulator? How do I define that? It's a somewhat fuzzy notion. Actually, Bob Laughlin, who is generally recognized as one of the best and the brightest in the field, even by Phil Anderson, was arguing that Mott insulators do not exist at all. So they exist in paper, but not in nature. So what I mean by that? Well, there is a 2D Hubbard model where we start from something that looks like tight binding, but then we add ad hoc by hand a large on-site Coulomb repulsion, U. And this has to be large enough. I mean, in mathematics, you can make it infinitely large, but the point is it needs to be larger than the bandwidth, the width of the relevant electron band, and then this becomes the dominant energy scale, and the behavior changes quantitatively. Now there are two leading contending variants: single band, 3-band model. The single band model in simplest variant has just a square lattice, and you have a hopping integral T, and then you have exchange J, and that's all you have. The experimental support for that is that according to ARPES, in Lanthimos-Thomson-Couperet, there is really one band that crosses Fermi surface, and there is only a single Fermi surface. But then experimentally, again, more than 30 years ago, beautiful experiments by Jörg Fink at Karlsruhe using electron energy loss spectroscopy. He showed that holes are actually not sitting on copper, they are sitting on oxygen more or less. Or at least 80% of the whole spectral weight was coming from oxygen. And that means that in this plaquette where you have coppers and oxygen, there is a hopping integral matrix element, which is hopping from copper to oxygen that is actually crucial. And that's a justification for three-band model. It doesn't have to be a hover. You can do a three-band tight binding model, but what I'm talking about not insulators here. So to make it a three-band hover model, again, you add this large U to it, and it has to be dominant energy scale. And you can voice many reservations about this model. First, that it is ad hoc. The Drude model and Landau-Fermi liquid theory were theoretically justified by starting from exact Hamiltonian, which we know, we just cannot solve it with 10 to the 23 electrons. But you could do some mathematical trickery, which Landau did, and to show that in some approximation, when you're coming close to the Fermi surface, then you have this theory. Nothing like that was ever done, to the best of my knowledge, to the Hubbard model. So it's a toy model, it's an ad hoc model. It ignores phonons, it ignores the ionic charge reservoir. When you allow it to be doped, it is not even thermodynamically viable. As you add more and more charges, if you make the system infinite, the energy will go to infinity. And then we have this issue of multi-layer cuprates, where certainly there are more bands. They are coming from different layers. And in a beautiful talk by Xinjiang Zhou, he showed very clear signatures of band hybridization. In a bilayer Bisco, you have bonding and anti-bonding bands. And if you have tri-layer, then you have three of these. Now, question is whether this is essential or it is just a complication. And people who push the single band Hubbard model or three-band Hubbard model, they would say it's just a complication. So you don't need that to explain high TC. Now, what do experiments say about this U and J? Well, Seamus Davis showed a beautiful experiment where he was using STM, scanning time microscope with a superconducting tip, and was monitoring the pair tunneling. It was incoherent pair tunneling, not a Josephson tunneling. And he inferred from that somehow the superfluid carrier density, and also from the spectroscopy inferred the value of the charge transfer gap. And then he found that the superfluid carrier density determined this way scales with the charge transfer gap, and therefore it should scale with J. Amit Keren, in his talk, presented evidence that in his material, which name of which I cannot even pronounce, is that TC actually scales with J. And there was a little bit of debate. Seamus was saying TC is not a good proxy for superfluid carrier density. I don't know what he meant by that, but what we know experimentally is that TC in fact scales with superfluid carrier density. And to the extent that if you tell me the superfluid carrier density in your sample, I will tell you what TC is, and you don't even tell me whether it's lanthanum strontium cuprate or YBCO, whether it's underdoped or overdoped. But there are some more caveats. One is that in lanthanum strontium cuprate, when we go from optimum doping to all the way to the overdoped side, there is very little change of the C-axis lattice constant and in-plane lattice constant and the copper to apical oxygen bond. So this hopping integral should not change actually. On the other hand, if anything, the charge transfer gap shrinks if it doesn't disappear. Experimentally, we can a better way to measure J is to look at the paramagnetic spectrum at pi over A, and that was measured by Mark Dean in LSCO films grown by LMB. And what was found is that the spectrum actually didn't change from undoped lanthanum cuprate all the way to metallic and non-superconducting LSCO. But at the same time, both TC and superfluid carrier density decrease, and they actually disappear. They go to zero at the critical doping on the right-hand side of the dome. And the second thing is that, second caveat is that superfluid density is not equal to the pair density. How do we know that? Well, there was this shot noise experiment by Doug Natelson that showed that incoherent pairs are present in lanthanum strontium cuprate at temperatures much higher than TC, and more shockingly, at energies which are twice or more above the superconducting gap energy. And that means that the superfluid carrier density is not equal to the pair density. It's much, much smaller. And then the third thing that also falls from various spectroscopies is that upon pair breaking, the superconducting gap does not shrink, it fills in. And altogether, all this that I have just counted, it looks certainly much more like BEC than like BCS. But I want to emphasize that it is definitely not a standard BEC either, because in that theory and in any two-fluid model, at zero temperature, you have quenched all the excitations, so all the normal state carriers must be in the superfluid. But that's not experimentally the case. So any two-fluid model failed. And in fact, actually any mean field description failed. Now, another point of controversy was, are cuprates homogeneous or inhomogeneous, phase separate? And certainly some of them are very homogeneous and can be phase separate. But the question is this necessary or is it just, complication? In other words, if you just want to explain the theory of high T, the mechanism of high TC theoretically, can we just work with a homogeneous, one band or two band, three band model, or we need to build in the phase separation from the beginning? And experimentally, what was shown at this conference was by Seamus Davis is that while pseudogap is very homogeneous, actually it varies on a scale of a couple of nanometers, and it can vary by a factor of 2 or more. However, the superfluid measured by in the same sample with the same technique is actually quite homogeneous. Now, the STM scale is typically, 100 nanometers or less. But my group has shown mutual inductance data showing that in the best lanthanum strontium cuprate films, the variations of TC are less than 0.1 Kelvin out of 40, which is less than 0.2%. And that's on the scale of 1 centimeter. Just to show some figure, okay, these are raw experimental data. They were not even normalized by dividing the transmission to that of the substrate, and you can see that the sharpness of this peak is like a fraction of a Kelvin, and if we had two parts with TC differed by more than 0.1 Kelvin, then we'll see splitting of this peak, which is not seen. So what's the grand total of all of this is that in my judgment, the problem of high TC in cuprate is still very much open, and it is still very much important. Why? First, because it's a challenge, like climbing Mount Everest or solving the Fermat's last theorem. The second is because if we really, really understand it, that would definitely advance condensed matter physics to a new level, and it may even spill beyond condensed matter physics. Remember, the Higgs boson, was actually following the idea from Phil Anderson on broken symmetry and Goldson mode, and Goldson mode acquiring the mass, which Higgs acknowledged himself. And last but not least, once we understand what's going on in cuprates, that may hint to us at where to look for room temperature superconductivity. RTS now needs to be replaced by a different acronym. Maybe we should say RT PS or AS for room temperature and pressure superconductivity or ambient superconductivity. We have room temperature superconductivity, or at least reported in hydrides, but only at millions of atmospheres. What we really are looking for is something at 1 atmosphere. But so far, theory did not really help much in predicting where to look and discover higher TC at ambient pressure. So how to move forward? I think for theory, I would encourage theorists to be bold and throw some crazy, far-fetched ideas about where to look at higher C based on plausibility arguments. New ideas in this field have been very scarce. So some theorists long ago proposed that nickelates should be high-temperature superconductors, if doped properly, to look like cuprates. And indeed, after some couple decades, it was observed. Not high TC, less than 10 Kelvin so far, but still something. On the experimental sides, I think first and foremost, we need to push the technique further. And there were at this conference several beautiful examples. Xinjiang Zhou showed spectacular advances in laser-based ARPES, pushing the resolution from 5 millielectron volts down to less than a millielectron volt, perhaps 0.1 millielectron volt, and then measuring at 10 millikelvin dilution for each spin resolve, time resolve, and so on. Seamus Davis showed STM with a superconducting tip operating in a dilution fridge, and Haiku Van just some hour ago showed spin polarized STM measurements, and these are new types of measurement, new hardware, and it's spitting valuable new information. Now, downside to all this work, if you look carefully, is that they were still working with the same old tired visco, after more than 30 years. That's because it cleaves, and you can do STM, you can ARPES, which are surface sensitive. But we need much more. How do we get there? Well, one path, which may not be the simplest, would be to integrate NB and ARPES or NB and STM. And then you grow by STM, and under UHV transfer it to ARPES or STM. I proposed this in 92, but it was declared crazy. Actually, as recent as 2010, our proposals from BNL to build the NB plus ARPES plus STM system were turned down because referees will say it's impossible, it cannot be done. Nevertheless, Davor Pavuna, who is regrettably not listening to this, followed this suggestion, and in late 90s built a PLD system integrated with ARPES at the Wisconsin synchrotron. And then a few years later, he built a tabletop one at Epafel in Lausanne. And they produced some in situ interesting ARPES data on LASCO, for example. Now, our BNL proposal was finally funded in 2014 or 15. And then within a couple of years, we built it, and it's working beautifully. There is a MBE machine and ARPES and STM all coupled together. And at Yale, we have something else, MBE integrated with LEAM, PIM, and LEAD. And there are, by now, dozens of MBE plus ARPES systems, or MBE plus STM systems built in US, in China, in Taiwan, etc. Some combine all three, some add PLD, some add sputtering, some add other analytical tools. The fashion has changed. If you talk about quantum phase transition, I underwent one from being obviously wrong to being obvious. By now, if you propose to build a new ARPES or STM system without NMB system, people will say that's crazy. Just not to be showing, just to show some pictures, not just words. Okay, so this is how these things look like in real space. And some people would argue these things are expensive. So this first NB system cost maybe $5 million. But I would say, while they are somewhat complex and expensive, per Nature paper, they are 100 or 1,000 times less expensive than a synchrotron or than a collider. We need new quantum materials. What has been done? What was being reported here? Well, I was following mostly the high TC line, so I cannot comment about non-superconducting materials, but certainly in terms of new high-temperature superconductors, there was not much. Maybe a couple of USOs reported in the last couple of years. So clearly much more effort is needed. And I understand very well that that is a high-risk endeavor, and so should the funding agency understand. You can spend years and not find anything, but we cannot afford not to look. The potential rewards are very, very high. We could argue that significant new advances have been made in synthesis of artificial metastable metamaterials like heterostructures and superlattices. This is one example, is this lanthanum-strontium cuprate, lanthanum-strontium superlattice. This is new, and you can argue that's a novel metastable material, and it's high-temperature superconductor. It brings in some interesting new physics. What is the importance here? The ARPES and STM are surface-sensitive techniques, and we know from Material Science 101 that every ionic material will reconstruct at the surface because the Madelung cohesion energy is long range, and the surface is seeing half of Madelung energy from the middle of the sample. Therefore, lanthanum, strontium, cuprate, YBC, etc., they all reconstruct in the surface. And this reconstruction is not seen in the bulk. So bulk is different from the surface. Now, in heterostructures, we can bury the interface, and we can bury it between materials which are ionic with similar charges, and thus one has a chance to make these interfaces perfect if you pick up your materials right. And therefore, we can be seeing, like in SAS tunneling, we maybe see something which is more extrinsic and not affected by surface schmutz. So what's the take-home message to the young scientists who will inherit the world? Well, first, trying something new. If you keep doing the same and you're using the same and with the same, then most likely you will get the same. In Alaska, they have a proverb, if you are not the lead dog, the view is always the same. Then the second message is trying something risky. This is a quote from American baseball star. You miss 100% of the shots that you don't take. And then the last one is that science is a marathon, and turtle will beat Achilles in the long run. So never throw in the towel. Thank you very much.
I arrived at this site. I found about 250 oral talks on different topics at this conference. And so I was a bit frustrated because it's not possible to a single person like me, for instance, if just to focus only on the talks related to magnetism, to overview all of them, because I also interested in the talks of superconductivity, for instance. So nevertheless, it doesn't work again. No. Okay, so nevertheless, so I noted in my notebook, so about 36 talks, which I would be interested in. So from this sections present in the conference on topologically protected spin texture, interplay superconductivity magnetism, cryogenic magnum spintronics, complex oxide materials, van der Waals materials, and finally novel spin-dependent phenomena in two-dimensional materials and heterostructures. I failed to attend some of them because of the dilemma of the parallel session. It was not possible. But nonetheless, I got some subjective impressions, which I would like to show you in the next, say, 5-7 minutes. So there are trends visible in this conference, trends of research which can be grouped in 4, say, sub-subjects. One of them, what I call so natural bulk magnets, so that means these are condensed matter solids, three-dimensional crystallographic structure, three-dimensional spin structures, big single crystals of different materials. The other extreme are artificial magnetic heterostructures. So this is a deposited or thin or monoatomic layers of magnets, bilayers, trilayers, or heterostructures of different kind. Somewhere in between, so there are so-called van der Waals magnets, which in some sense, so they exist in the bulks as bulk crystals, but they, in many cases, can be considered as natural heterostructures by virtue of the very weak van der Waals coupling between the magnetic layers in these kind of materials. And of course, a very interesting part of this conference was research on hybrid superconducting ferromagnetic systems. Because, well, actually, in this part of research, two most fundamental phenomena in condensed matter physics, superconductivity and magnetism, were brought together. Well, but just I want to show my personal impressions, just a few examples, say, from research on natural bulk magnet. There were several very interesting, for me, presentations. One of them, for instance, on this material, manganese silicium telluride, where it was shown a very interesting kind of colossal magnetoresistant effect, which is not related to the full polarization of the spin system, like, for instance, in the double exchange manganites, but it was argued so that a very strong magnetoresistant effect in small magnetic fields far away from the saturation magnetization is due to a novel kind of interaction which is caused by so-called chiral currents on the atomic scale, probably existing in the transition metal oxygen octaeders. A related, or more or less related, theoretical work on the chirality problem, on the chiral soliton lattice, was discussed in the talk of, in this talk presented by Bastignori from Spain, where the phase diagram was proposed where the chiral spin lattice could be controlled either by magnetic field or also by the applied current. And it turns out that it was predicted so that this chiral spin lattice could turn, it has a certain phase stability area, but it could be turned to the fully forced ferromagnetic states either by application of a stronger current or a stronger magnetic field beyond the critical value. But surprisingly, also when it increases the current further, so the ferromagnetic order is surprisingly destroyed. So possibly due to the enhanced spin fluctuations or spin waves in this particular regime. So also there were some presentations, one of them given by Gabriela Aurel about this very interesting magnetoelectric material, calcium, strontium, barium, copper oxide, where two order parameters, the magnetic order parameter, the ferromagnetic order parameter, and electric order parameter were brought together, and that, of course, causes some interesting new phenomena which were discussed in this talk. So now coming back to the artificial magnetic heterostructure, so skyrmions were omnipresent at this conference. In early form, in most of the talks, skyrmions or other topological magnetic structures were present and discussed. And there was an interesting visible trend in these presentations focusing on manipulation and control of these topological spin objects with electrical current in the multi-structures composed of these of the ferromagnetic material where skyrmions or, say, domain walls or magnetic bubbles could be generated and manipulated by the currents which run through the deposited, say, metallic layer or stripes with strong spin-orbit coupling, like, for instance, platinum. That was very nicely overviewed, I think it was today or yesterday, maybe today, in this plenary talk by Pietro Gambardella on manipulation of chiral spin textures, and related talk by Saul Feliz on this current-driven dynamics of Néel domain walls. Well, also manipulation of the skyrmions in 3 layers. So this kind of magnetic 3 layers was highlighted in the talk by Karen Evershaw-Sitte today on how one can control, for instance, the skyrmion Hall effect to enhance it, to suppress it, and to manipulate with this kind of interesting transport phenomenon. One shouldn't forget, so another interesting theoretical presentation, because, so you see, so this conference is on quantum material, but also on quantum technologies. Therefore, the people that start thinking on not only some fundamental understanding of this magnetic phenomena, but also on possible future technological application. And one of those was presented in the talk by Andrei Slavin, who proposed a very interesting concept of a generator of monochromatic terahertz waves. So actually, at present, so generation of terahertz radiation, in particular monochromatic radiation, is a big problem. And this concept suggests to make a bilayer structure of the conductor. So this is platinum conductor and a conventional antiferromagnet nickel oxide. And so by running the current through platinum, so generates a spin torque, which generates monochromatic terahertz radiation in this antiferromagnet. So next, actually, so this is also one contribution about the stabilization not only of the skyrmions, but also the antipodes, so to say, antiparticles, so antiskyrmions, given by Timo Schmidt from the University of Augsburg. So there were also materials presented in this conference which itself are not magnets, but so they provide interesting spin phenomena. And one of those presentations which I liked very much personally was the report on the spin-life anisotropy ultra-thin black phosphorus given in a plenary talk by Ahmed Afzar, I think on the first day of this conference, where it was found that, for instance, the spin transport is very anisotropic in this material. So it's very different if it runs along the edge, along the zigzag edge or along the armchair edge. And more importantly, it was found that the spin relaxation length in this single layer of black phosphorus is extremely long. It amounts to several microns, which is really very spectacular observation. Another kind of heterostructure where these chiral interactions were considered and experimentally observed is a multi-layer built out of a ferromagnetic strontium ruthenium oxide separated by thin layers of non-magnetic strontium titanate. The magnetic structure of this multi-rate was revealed to be of the spiral character, and it was argued that this is a novel kind of phonon-mediated interlayer exchange which gives rise to these non-collinear spin structures. So, coming to the other research areas, so these quasi-two-dimensional van der Waals magnets, several of them were presented in this conference. And there was a very interesting plenary talk given by Aguj Gulzaren on the magnetic properties of 2D layer materials, where a family of these transition metal ion carbides or nitrides were presented and classified with the aid of the density functional theory, classifying them into having, say, ferromagnetic order state, antiferromagnetic order ground state, and the kind of anisotropy, easy plane or easy axis. So that was a very interesting presentation. But there were also really a series of interesting experimental talks. One of them, that was a Today talk, an overview given by Man Hong Fan on the exchange bias and on the interface-related effect in the two-dimensional van der Waals magnetic heterostructures, which is important in two aspects. The one is that one could, the one important aspect is the generation of this exchange bias. So that means the shifting of this hysteresis curve in the desired direction in this, with regard to the zero magnetic field. This is important, say, for the memory storage devices. On the other hand, the enhancement of the critical temperature of the van der Waals magnet, it was shown, for instance, a very spectacular enhancement of the critical Curie temperature of the vanadium diselenide, which was put on the substrate of molybdenum sulfide. And so the temperature, the critical temperature was raised up to the room temperature, and it was shown, so a very nice hysteretic magnetization curve measured at 300 Kelvin. So also a combination of, say, of non-trivial conductor, which is a graphene, with magnetic van der Waals material like transition metal dihydrogennates was illustrated in a talk by Juan Sierra from the Catalan Institute for Nanoscience and Nanotechnology, where they found so that the spin currents generated in with the aid of these ferromagnetic electrodes on this stripe of graphene can be manipulated by the layer of the transition metal dihydrogenide in the presence of the applied magnetic field, where one can change at will the spin polarization of the carbon from the out of plane and turn it to the desired angle depending on the field strength applied to this interesting to this bilayer structure. And in this case, of course, so the anisotropy of the spin lifetimes was found, and it is very strong for certain experimental conditions. One particular material from this family of two quasi-two-dimensional van der Waals magnets has attracted special attention, and that was chromium germanium telluride, because of its robust ferromagnetic order, even in the few layers limit, which is not very often found in this kind of materials. And for instance, so this specific very useful property was used in the Josephson junction structure discussed by Hiroshi Iduchi from the University of Tokyo in Japan, where they succeeded to fabricate a structure which shows a very unusual Josephson effect. So the superconducting part was made out of niobium diselenide, so this is a non-heterosymmetric superconductor with a strong spin-orbit coupling, and it was observed a very interesting tunneling of this of the copper pairs with an unusual phase shift. So actually, they also found a very interesting phenomenon of enhancement of the critical temperature of this material deposited on the special tensile substrate, which expands the crystal lattice. And actually, so by definition, I had to attend my own talk on this subject, where we reported on the pressure-dependent change of the magnetism in this material, namely the suppression of the ferromagnetic order by applying a compressive strain. And therefore, that was a really good interplay with the results of Dr. Iduchi, where they found so that if one expands the structure, so the ferromagnetic order gets more stable. Another interesting, so to say, application of the single layer of chromium germanium telluride was discussed by Klaus Zollner from the University of Regensburg in Germany, where he showed so that when this layer is put on the graphene layer, and the twist angle between these two layers could be changed, it leads to a very interesting change in the band structure of the graphene. So where this Dirac cones could be gapped, and this could change. So this is the topology from the trivial to non-trivial and back. That was in fact very interesting functionality of this chromium germanium telluride layer. So last but not least, of course, so this is a hybrid superconducting ferromagnetic system. So in this case, actually, in my opinion, so the magnets, they play a secondary role, because the most focus is to find the most interesting spectacular phenomena in the superconductor, like, for instance, topological superconductivity, the emergence of the Majorana fermions and Majorana modes, but also a feedback from a superconductor to the magnet was actually very interesting. And that was nicely demonstrated by the plenary talk of Roland Wiesendanger from the University of Hamburg, where they showed that, for instance, they build up a spin chain of manganese atom by atom on a layer on the surface of the superconducting niobium. So this is the chain, and so they studied the electronic structure of this chain. And it turns out that that due to the hybridization of the electronic state of the superconductor with the electronic state of the magnet, so under certain conditions, a special modulation of the electronic structure in the magnetic chain takes place, and more importantly, so a coherent states at the end of the chains are formed within the superconducting gap. And so actually the idea is to move these states to the close to the Fermi energy to realize these Majorana bound states. So another interesting superconducting ferromagnetic system was actually, in my opinion, again, a superconducting Josephson junction made of high temperature superconductor, YBCO, separated by a very thick layer, ferromagnetic layer of lanthanum strontium manganese oxide. And still, so the thickness of this layer was extremely large. So there was some microns, but still they could nicely observe a Josephson effect on this kind of system. So this is really a very interesting experimental observation. One more presentation, more in the direction of the technological application, were hybrid structures made of a ferromagnet, platinum, and a superconductor. So the idea was that as soon as one has a vortex state in a superconductor, so this is kind of periodic topological lattice, and if one put it into contact with a ferromagnet, so then if one matches the periodicity of the spin waves excited in this ferromagnet with the periodicity of the vortex lattice, they should interact. And in this work, so this Alexander Dobrovolsky from the University of Vienna has shown that indeed, so they can bring this vortex lattice and the spin waves in that regime where they start interacting. And really, amazingly, so if they then apply a current to the superconducting layer and start to move in vortices, they start to move very, very large velocity. And this gives rise to the generation of so-called exchange spin waves in a ferromagnet. So these are very unusual kind of spin waves, which have a very short wavelength. And it was shown that they don't form as it usually happens in a ferromagnet, so the standing waves, which doesn't transfer any energy. But that was a monodirectional propagation of this, of these exchange spin waves, which then can transfer energy. So I think with this overview, I'm at the end of my presentation, and in my personal opinion, and I think that you would share this opinion. So this conference was a great success, and of course, then we have to thank this local organization team headed by Ali Ganser for this really great event in the condensed matter community, in the community of magnetism and superconductivity. Thank you very much for your attention.
Thank you.
So I don't think so that you have questions because I just transmitted to you so the results of other participants.
Good evening, everyone. So Prof. Vladislav have already summarized quite well with the spintonics and also a bit towards the end, the topological superconducting part. So unfortunately, because of some emergency, I couldn't have chance to really summarize, so I talked to Prof. Ali Genca. So I decided to give a short presentation on something that we have been doing over the last 2-3 years, and it's a kind of a new direction in the field of like two-dimensional magnetism, but this was not covered in this one, so in this conference, so we thought that maybe it could be a good kind of addition. So we are, as I mentioned, we are working with the two-dimensional materials, and now I will be telling you about the story of the material that we are working. It's called platinum diselenide. And this material is a non-magnetic material in the ultra-thin film limit. So by creating some defects, I will be showing you that we can turn this material into a magnetic material. And it has very distinct magnetic properties like layer-dependent magnetism, etc. And this kind of research was not covered in this novel spintonics aspect part of the ICQMT. So I thought that it could be a good addition. So this is a kind of a material made of like platinum and then sandwiched by the selenium atoms. So the material has very, very distinct electronic properties. This material is a semi-metal. Once it has a thickness above 4 layers. And whenever you thin the material down, the material is becoming a semiconductor. And the material becomes a very good insulator once you reach to the monolayer. And but one thing that we were quite interested with this material was the materials showing there were lots of calculations that if you can kick out some metal vacancies, in this case the platinum, you could kick in some magnetism in this material. And creating this kind of metallic vacancy in this material is slightly easier because of the lower formation energies compared to the other materials, to the semiconductors, which similar physics was predicted. And the question was like, do we have this kind of defects? So these two-dimensional materials, they are just surfaces. We have lots of defects on these materials generally. And in the case of the platinum diselenide, we had a defect concentration, platinum vacancy concentration of the defect up to 10 to the power 13. And these results were also confirmed by another independent study with some STM analysis that the material is like full of the defects. And we made lots of devices, and nearly the half of the devices that we studied, the material is supposed to be non-magnetic in the pristine form. And we could see the kind of the very hysteretic magnetic resistance in this device, at least the half of the samples that we studied with a Curie temperature around 13 Kelvin. And whenever we were focusing on the other part of the other devices, basically it was showing kind of like a zero antiferromagnetic ground state ordering at the zero field. But whenever we were applying more fields above the coercive field, the material was getting fully spin polarized. So it's kind of an antiferromagnetic type behavior. So what we were seeing is like nearly the half of the device that we studied was giving the response of the ferromagnetic response, and half of them was giving a kind of antiferromagnetic response. And the question we tried to answer is there any layer-dependent magnetism in this material? And for that, we compared the magnetic transport properties of two devices, but with the thickness of 1 layer difference only. And whenever we studied the magnetic transport properties of these devices, and they were showing the ferromagnetic and antiferromagnetic response. So they were just like 1 layer dependent, 1 layer difference in these crystals, and then we were already seeing like completely different magnetic transport behavior. And we tried to understand, and this phenomena was only visible for the crystals less than 14 nanometer. And whenever you go a bit thicker, you don't see any of these effects. And the MR was decreasing. And we had like more detailed studies, but basically what we do see is like in the material, you have like ferromagnetic or antiferromagnetic ground state ordering, and then by just adding or removing one layer, the material turns into a ferromagnet. And whenever you go above 14 nanometer, the material becomes a non-magnetic material. And so we explained this with the ICQY interaction, and basically these magnetic moments formed due to these platinum vacancies is giving the magnetism, and all these thickness-dependent measurements are in good agreement. So, and then we studied also if the monolayers and bilayers of this defective material is also magnetic, and we do see like similarly layer-dependent magnetism down to monolayer in this material. And so I'm a material scientist, and we are very interested in manipulating the materials. And one of the things we are quite interested in nowadays is like modulating this kind of magnetism at the ultra-thin limit. So there are lots of predictions by tuning or modulating the defect concentration of the platinum atoms in these defects in this material. We can increase this relatively low Curie temperature of 13 Kelvin to up to room temperature. Or we have also another approach motivated by some calculations. If you can dope your material with the transition metal odd atoms, you can again increase the Curie temperature. And the good thing is like, all the talks that you have seen about with the two-dimensional materials in this conference were from the intrinsic magnets, meaning that their bulk form, their mother form is also a magnet. But this platinum dicyanide and also the other materials that I will be showing, these are non-magnetic in the pristine form, in the bulk form, and you need to thin it down, and then you need to create some defects. And platinum dicyanide is not alone, so there are lots of materials which shows this kind of defect in this magnetism in the monolayer limit. And one of them was just, for example, this was just published 2-3 weeks ago, chromium sulfide bromide, which shows again this kind of defect in this magnetism. And there was also another study on the molybdenum ditelluride, which was also showing a defect in this magnetism up to 100 Kelvin. And we have lots of new candidates, and lots of new predictions are happening that if you have these ultra-thin materials and create some defects in them, you can turn many of these non-magnetic materials into magnetic, and some of them are even like layer dependent. The magnetic properties are depending on the layer. Yeah, so this was done while I was working with Prof. Andreschkis at EPFL, but we are now pushing more towards the manipulating the low Curie temperature of this kind of defect in this magnetism. And one of the key aspects of these magnets are they are highly air stable, and any of these two magnets that you have seen in this conference, they are very air sensitive. So meaning that if you would just produce and leave on the table, the material would just disappear within a few minutes. But this defect in this magnetism that I showed, the material systems, they are highly air stable. So this could be a way of like engineering the magnetism in the ultra thin limits, and they can be integrated with the spintonics devices. So thank you very much, and yeah, so that's all from me.
Thank you. We had an excellent talk by Professor Jorge Ignacio La Torre before, so I will restrict myself to something very brief, which is to quickly summarize what 3 representatives from 3 companies have said here, and you have this information also in the YouTube channel of the conference. So first, I would refer to Thomas Ortlep's lecture or comments from, he's from CIS, Forschung Institute für Mikrosensorik in Germany. And he claimed he was managing 120 people working from the viewpoint of taking results from science projects into innovative applications. And, but their business core basically was on classical technology. They, however, had 3 activities dealing with quantum technologies, and they were searching for new apps in quantum technologies from what they see scientifically in scientific developments. And basically the first application that he mentioned was a quantum-based gravimeter as a sensor to detect holes and other undesired features underneath the Earth. And this worked in a quantum regime. And it had been proposed by a UK group about 10 years before, but it had been proposed as a 2 by 2 meter table, optical table solution. And their advancement is that they made this a 2 by 2 centimeter sensor. And they have the first 150 orders from the German government in order to investigate soil in new development construction areas. The second one that he talked about was diamond-based magnetic field sensor, which is calibration-free in operation, and it's very difficult to manipulate. So they already have 1,500 orders for this, and the main application apparently is in smart meters that detect manipulation from non-specialists. And the third one is on solid-state circuits based on Josephson junctions, I believe. And in this case, their business is related to the system integration, and this is dedicated to the assembly of the quantum system in smart attachments of optical fibers and transmission and packaging and so on. So that's basically, in some way, there are hybrid applications of quantum systems. And he warned also that there's too much hype scientifically, as Professor Alatorre said before, and that we must be careful, that we must find quantum technology applications within the next 2 or 3 years, or at least they should be addressable. And the second speaker that I give you a summary of is Joanna Skiba. She's from Toshiba in the UK, and she talked about their efforts in building devices with applications in quantum networks, and based on the use of entangled photons. And she talked about the development of materials from discovery to manufacturing, and they were using QDATs. They were using QDATs, side control QDATs, droplet QDATs, and side control droplet QDATs, which were the ones that they have been most successful with. And their applications basically were on entangled photon LEDs for quantum internet, where she said that there should be a drastic change in the coming years, for quantum encryption in classical communications, for quantum sensing, and also for remote programs of quantum sensing. And this based on quantum relays as basic elements. They try to reduce the error rate for intermediate distance transmission. And for example, they have I believe, I understood they have demonstrated this entangled photon transmission over metropolitan areas, which were of the order of 18 kilometers. So, and their effort is now to expand the capability of quantum communication on intrinsic security, longer communication distance, and higher efficiency. And now to finish, the third participant from a company was Valery Vinokur, and he's from Terra Quantum in Switzerland. And he talked about quantum computing and security. And basically, there were 3 integral areas where he said which they are addressing. One is on quantum algorithms, which is a hybrid technology, quantum computing, which is hybrid quantum cloud and quantum, what they call quantum MWare, and quantum security. So he claimed also that they can basically, I don't know if this is now or this is coming soon, they can secure 100% so they can make 100% secure storage and communication data. And what they do is they enhance classical approaches in 3 key spaces. One is optimization, another one is machine learning, and the other one is simulation. And I think he talked also about a paradigm shift related to irreversibility. And he gave an example where there's an instant going back in time, and that this is their philosophy, to protect circuits, so or protect transmission. And he also talked, just to finalize, about novel superconducting qubits, which he believed would work at the temperatures of 10 Kelvin. So I think that's more or less what I think was most, probably I left many things out, but I thought that some of them would be, as they were before in the magnetic materials, would be revised from the point of view of the quantum materials development. So I did not want to duplicate that, and I wanted to be as short as possible. So I must congratulate all the, from my point of view, all the organizers of the conference for an excellent job, and thank you very much.
Well, I think I took notes, okay? I just want to say a few words because I don't want to take much of your time. There are 2 issues that I have taken a note. One is that quantum technologies require cryogenic technology. So without cryogenic technology, maybe photonics could be an exception in one of 5 technologies for qubits. And to achieve low temperatures, we need high purity helium gas. Helium is unfortunately very expensive and has become more and more expensive. Even in developed countries, there is a problem of helium contamination. So even if you have very high-tech dilution refrigerator to achieve these temperatures, if you have a contaminated helium gas and you liquefy it with helium-3, it's very, very expensive. And this is another technical issue that some developing countries may have real problems with this helium because they prefer to buy low-cost helium, which cannot be pure helium. The other issue I just would like to say, as a comment, superconductivity prototypes, qubit systems for quantum computation, quantum computers. And Professor Latorre has given a very comprehensive review. This is just a comment that we are still relying on what Brian Josephson discovered as a Josephson junction in 1962. And there are maybe more than 6,000 superconductors have been discovered since then. So Brian Josephson, as a Nobel awardee, let's say, he was an undergraduate student when he made this Josephson junction. So making Josephson junction is not a real issue. And there are purities and impurities associated with the coherence time and decoherence time. So this is, as Latorre indicated, is a very critical issue for the robust systems to be constructed. So I don't want to take your time, but I think this was to be noted in the conference overview, so I just wanted to add these two things. And the other thing, as an organizer, and this has been maybe, I'm not making overstatement, is the history of science and technology, of quantum technologies, initiated in Turkey with the minimum lowest funding in the area. Ever since the announcements of Nobel Prize just a little more than 2 weeks ago. You made it, and I'm sure this conference will be one of the tops in the next coming years. And in terms of quality of research, and also in terms of participation from many different countries. And the other thing that we must also consider, participation of scientists where science is underrepresented to this conference. And we need those people in the conference. And with the limited budget, we have tried to make this. And we will continue supporting people from the underdeveloped world. And with your support, the main income of the conference is registration fees. And hope that we will have many sponsors in the next edition of this conference. And we will keep continuing finding the ways of living in peace in the whole world. Because advancements in the technology sometimes may give some big power to politicians, which may ruin the whole world. Thank you very much. The Intermac, which is a well-established conference on magnetism, but applied magnetism. I think it's the best time for us to stay in the same venue here. May will be better than October, we say. And in ICSM, we would like to keep maybe more short focused on quantum materials and technologies to keep the overlap minimum. So you are all welcome, and you will probably make it to come again. So this is so I don't have the statistics of the conference. Roughly speaking, we have 308 registered participants, and some of them online. And one thing we did not ask for approval, that all the presentations are now on YouTube. Next time, for the second edition, we will make sure that these will still be on YouTube, but the passport protection will work. So everyone will be able to join the conference, either online or in person, using password with security measures. So this will be our second contribution to the conference. So I think we better go to welcome party. If there is anybody else who would like to say something. Vladimir, you want to say something? Oh. Anybody? Okay, sorry. Okay, let's have Chris, okay.
There was a very interesting talk by Professor Zajkin today on quantum phase slips and fundamental theory of quantum phase slips in some reference to full counting statistics. So that just probably was not fully underlined in the conference summary. Thank you.
Okay, this will be noted, I think. Is it okay? One more? Right.
Okay, I just want to propose that we thank our chair, Ali, and those unsung heroes once again for this very successful conference. Okay. Yeah.